This presentation analyzes a paper on Potemkin understanding. The term refers to an LLM showing a superficial grasp of a concept, like a facade. The authors argue that testing LLMs with human benchmarks is flawed because LLMs can pass these tests without the deep understanding we'd expect from a person. The paper formalizes this issue and introduces two methods to measure its frequency, finding that this shallow understanding is a common problem. Figure 1 gives a concrete example of Potemkin understanding. An LLM first correctly defines an ABAB rhyme scheme, leading us to believe it understands. But then, it fails to apply that knowledge in a simple creative task. The most revealing part is that the model then correctly points out its own mistake when prompted. This internal contradiction, knowing the rule, failing to apply it, but recognizing the failure, is the signature of Potemkin understanding. This figure visualizes the theory behind Potemkins. Imagine interpretations as mental models. Humans have a few predictable ways they might get a concept wrong. A keystone is a test question designed to catch those specific human errors. If a human passes, we trust they get it. A Potemkin is when an LLM passes the keystone, but fails on other questions, revealing a non-human misunderstanding the test wasn't designed for. Section 3 presents the first of two experiments. The authors built a new dataset to test the gap between knowing and doing. They chose concepts from diverse fields like poetry and psychology to ensure the findings are general. For each concept, they first checked if the model could define it. Then, they tested if the model could classify, generate, or edit examples of it. The results were clear. Models are excellent at definitions, but poor at application. Section 4 presents a clever automated method. It's based on testing for incoherence. For example, they'd ask a model to write a haiku, then ask it in a new chat if the text it just wrote is a valid haiku. Often, the model contradicts itself. This inconsistency is then used to find Potemkins automatically. An LLM acts as both a student and its own grader. When the grader disagrees with the student, a Potemkin is found. This method underestimates the problem but still finds it to be very common. This figure shows the automated method at work. First, an LLM answers a textbook question about cousins correctly. It seems to know the concept. Then, it's asked to create a new related problem and solve it. In the final crucial step, it's asked to grade its own answer to the problem it just created. It marks its own answer as incorrect, a direct contradiction that reveals a shallow, incoherent understanding. To sum up, Potemkin understanding describes how an LLM can appear to know a concept while lacking true comprehension. This work shows that our current benchmarks, which were created for people, are not fit for purpose when evaluating LLMs. The authors provide a new theory and two practical methods to expose this shallow understanding. Their key finding is that this is not a rare glitch, but a common problem, urging a re-evaluation of how we measure AI progress.